So thank you for staying with us. Now I can tell you the truth. The truth is that if you explain to a biologist what I told you before, he will tell you you are completely mad, you are completely crazy. This is not at all what is a cancer and what is a biological problem. The real questions are much more related to questions of therapy and to questions of how cells adapt to the whatever, maybe the mechanics or whether what happens in the living tissue. And that's what I would like to say now, take a completely different point of view, which is what I would say is a real point of view of a biologist, which is to believe that what is driving life is mostly adaptation and selection and mutations. So the motivation of this series of questions we're asking is that nowadays 40% of cancers escape therapy. The reason is that the therapy now are very precisely targeted, and so they will kill a very specific type of cells depending on their genetic properties. And because of that, other cells will take over. And this obliges the doctor to change therapy or to use multiple therapy. And an idea which was used, which was very popular 10 years ago, was to say, okay, if we see a system of cells which are in some sense in competition with each other, why not to try to use this competition to fight cancer? Rather than trying to kill the cells, let's try to use the competition between cells to control the cancer without killing the cells. And this led to this point of view that cancer has to be considered as an ecology and an evolution property. And this is a book which was around that. Oh, you see this animal here and these whales. There is a contradiction, by the way, which makes that you have to think of cancer as in an evolution point of view. If you think that cancer occurs because cells have a risk to become tumorous, then if it was the case, big animals will have many cells, should have more cases of cells becoming tumorous and then more cancers. And it's not true. If you think of a mouse will live 3 or 4 years and then it will get a cancer. I don't know, but certainly some of you got mice when they were child. These animals do not live very long because usually they get a tumor and they die from it after 3 years, 4 years. If you think of whales, which are extremely big, they never get cancer. They die from anything, but they can survive 100 years without cancer. So which means that it's not true that cancer is proportional to your weight and to the number of cells. There's something else. There are regulations which results from the evolution of animals, which make that they resist to cancer. And this is all this book is about this. There is a small animal like that, which is not very big, which is a rat, which can live a long time, will never get cancer. An amazing animal which will never get a cancer. So biologists and medical doctors are very interested to understand why, what are the protections that these animals have. There is another question which is related to that, which is, of course, heterogeneity. So these cells, I tell you, cells can be very different, and when you kill one type of cell, other cells can come. There was there was in 10 years ago this paper which was very influential, saying basically it was saying in a biopsy, depending where you take the biopsy, you will get different types of genetic outcome. The heterology of the tumors make that a biopsy can be can give you different results depending where you take the cells. And then there was this question which was asked after that, why not use competition, if this is all true, to optimize therapy? And this is an ongoing research in medical science. So when you speak of evolution, an adaptation, you need a phenotype. So the idea is that cells have a phenotype, and not only location. So if you think of a phenotype, I call it Y. One way to settle the problem is to say, okay, your cells are dividing with a Lotka-Volterra rule, and there are three, and then you give therapy. So let's imagine that you have idealized a therapy in two types of therapies. One which reduce the growth, the birth of cells. So this R of Y is the birth of cells. One of them which will kill the cells. So this cytotoxic drug will kill the cells. And cells are in competition between themselves. So rho of T is the total number of cells, whatever is their phenotype, and they are in competition for resources. Okay? And so, depending on their phenotype, they will resist more or less to the cytostatic drug and to cytotoxic drug. And of course, you imagine that there are mutations are possible. Cells can give birth, when they divide, to more resistant cells. So you have here a possible term, this Laplacian in Y, giving you the mutations. So in this thing, what we have to keep in mind that Y is a phenotype for resistance to drug. So it's important to keep in mind that Y, so to keep in mind, Y equals 0 equal low resistance. So which means high proliferation. And this is because you assume some allocation of resources. Okay, so a cell has to decide if it will allocate its resources to proliferate or to resist to the poison, to the drug. So Y equal 1 is high resistance. And if it has resistance, it's low proliferation. Okay? So, if you solve on a computer this type of equation, and if you don't put a therapy, so which means that C is 0, what you get is you select cells which are of very low parameter Y. And the reason why you get that is simply that this term is positive. This one is more or less, it's not exactly 0 in the numerics, but more or less 0. So basically, when Y is very small, R is very big, and you have an exponential growth with a big term, of course, this will take over, and you will see only those which have the higher growth rate. So what you see is that you don't put therapy, you get cells which are highly proliferative, not resistance. And what we did here is put very resistant cells, and slowly they become, they change their phenotype to become highly proliferative. On the contrary, when you put a therapy, if you put cells which are normal cells, not very resistant, what you select is a phenotype of resistant cells, and at the end you see only cells which are resistant, and you have selected for the phenotype Y equal 1. So this is a phenomena which is very well documented in ecology. It is called the competitive exclusion principle. You always select the fittest. These kind of things, you can also observe that in experiments. So they have experiments where they express some proteins, which are, and then you get this kind of pictures showing that indeed you can select, even in vitro, even in vivo, you have a selection of cells with a certain phenotype measured by certain expressions of proteins. All this is very well known. There is a complete mathematical theory about that, which describes this selection of phenotypes, and you can create equations which will create, so this times is a phenotype, which will create speciations where you have two type of individuals with two type of phenotypes will survive, and eventually branching later where you have 4 individuals, or this kind of pictures where you create many phenotypes which can survive together. So this is very well documented. There is a very large literature, both in probability and in PDEs. If you look at small number of individuals, you will do it from a probabilistic point of view. If you look at large populations, then there is a continuum limit that you can establish from the large population limit of probabilistic models, and you get these equations that I mentioned here. So what is the mathematics you do about that? The mathematics is the following. If you keep, so what you have to say is that cells are dividing and they are slowly changing their phenotypes. So there is a scale, which is a scale of the cell division, and there is a scale, let's say 1 day, and there is a scale of the evolution of the phenotype, which is, let's say 10 days or 1 month. And so you introduce a small parameter which tells you that the time scale for evolution of phenotype is not the same time scale than for division. And you create that. And what you prove with technical assumptions, I don't want to do it here, is that typically the limit of this equation will always be a Dirac mass. So this is the exclusion principle. You always select for the fittest. The fittest is not always the same according to time, because in this time scale, the phenotype is evolving. We are in the time scale where you see the evolution of the phenotype. So you see that you have a fittest, which is y bar of t, and you select for this fittest for all the times. And not only that, but we know the equation that is satisfied by y bar. It's not an easy characterization. If you want to y bar, what you should do is compute the solution of an aconal equation, an Hamilton-Jacobi equation with constraint. So it's not the usual Hamilton-Jacobi equation that you find in quantum mechanics or in large deviations. It's another equation which has the same flavor, except it contains the weight, the total population, rho bar of t. The weight of this Dirac mass is a parameter, and this parameter is a Lagrange multiplier for a constraint that the maximum of phi should be 0. And I don't remember if it's, and the reason of that is that the phi comes by the idea that an epsilon looks like a Dirac mass. If you think that your population is very close to the fittest rate, what you think is that if I put here your phenotype, which I call Y, your population is something like that. And this is Y bar of T. And if it's like a Dirac mass, you see the Dirac mass is not far from the exponential minus Y bar squared over 2 epsilon, where epsilon is a temperature. So there is a rho bar here, and square root of 2 pi epsilon if you are in dimension 1. So you believe that you are close to that. And so rather than computing a Dirac mass, which is nobody likes to use these kind of things in practice, you compute the polynomial. And the phi is a polynomial which is here. And a polynomial is nice. So this is the logic behind that. And of course, if you have here a polynomial, it has to be 0 at Y bar. So this is the reason why you say that phi is 0 at Y bar. Okay. You get, these are viscosity solutions. If you know that the singularities do not care, there is unique solution. What could happen? What is not very clear is what happens initially. If you don't put initially something which is like a Dirac mass, it's not clear where it will happen, this selection. So it will happen somewhere, but it's difficult to predict where it is. So if you know where it is, okay, this is what we computed here. Here we put a Dirac mass here, and the Dirac mass is moving to this point. And here we put the Dirac mass here, and you see it moving to this point. If you put it in the middle like a function, it will pop up somewhere. But in any case, this kind of equation select for a Dirac mass. And for a single, usually. Except symmetry or very exceptional situation, you will get a single Dirac mass. Okay, so this is what the theorem tells you. So these are viscosity solutions in the sense of diurnal ions, because you have an Hamilton-Jacobi equation, you know that it can have singularities. Beyond the singularities, they are not unique, but there is a selection, because it comes from a parabolic scale. You have a selection of the correct one, which is a viscosity solution, which is not the one you get when you do high frequency in wave equation or Schrödinger equations. It's a different solution you would get. One of the questions we're interested, and we are not very happy of the answers we have, is to explain this kind of drawing of picture where you have two nutrients. You can see that of a system where you have two nutrients. You have a population which can use the two nutrients. You have a Dirac mass, and at certain points, the Dirac mass splits in two Dirac masses, and you can interpret it in the following way. At the beginning, your population is using the two nutrients in the best way, and suddenly, the adaptation makes that it's better to have two type of populations which are adapted to the two nutrients. So this population here has been monomorphic, and then it splits in a dimorphic population. One of them goes to the nutrient 1, the other one goes to the other nutrient. So this can happen if you have two nutrients. So if you put 3 nutrients, you can have 3 branches. If you could put 4 nutrients, you can put 4 branches. If you put 1,000 nutrients, you could have 1,000 branches. If you put a continuous set of nutrients, What do you observe? Who knows? Well, who would you say? Do you know species which evolve continuously from a dog from a dog to a cat? No, I don't know. I've never seen. So whatever, nature will always select for very separated phenotypes, even if there is a continuous level of nutrients which occurs in nature. If you think of oceans, in oceans everything is uniform, everything is mixed up, so you have all the possible food, and you see very, very well separated species. So this is what you see in the models I showed before. So these are the questions you ask in this theory of evolution. What we showed is now that if you go back to this problem of cytotoxic and cytostatic drugs, so you have two drugs, and you want to know how I should give the drugs to the patient. We imagine two protocols. One is that you give a constant cytotoxic drug. The cytotoxic drug was, let's go back to here. The cytotoxic is the one which kills. The cytostatic is the one which prevents proliferation. If you do a constant cytotoxic drug with a periodic cytostatic drug, what you observe is that the phenotype increases and you get resistant cells and you don't kill the tumor. With the same dose, if you make it constant cytostatic, periodic cytotoxic, you are much more efficient. And then you kill the tumor and you don't see the resistance occurring. Okay? So this effect exists and you can observe it with this model. People have been very further than that. There are works which explain exactly what is then you can say, okay, let's optimize the therapy. So you enter in the world of optimal control. This is a beautiful optimal control problem. You can optimize, and then you can find the optimal therapy for that, which is to get to give the cytostatic at the end and cytotoxic at the beginning. So this is the optimal protocol according to control theory. So these questions you can ask by mathematical models and using tools from different areas, including optimal control. The second thing you can ask is you can try to be coherent and say, okay, from one side you have a mechanical model which tells you that the distribution of cells in space is important. This is what people from biomechanics believe. You have biologists who believe that the phenotypes are more important and that the biology is phenotypes. So you can make a mixture of the two and say, finally, we have a space and a phenotype. Okay? And you can say, let's simplify. A tumor is a spheroid, it's symmetry. Let's take the radius as a parameter for space. Okay? Or between 0 and 1. So now the problem becomes much more tricky. You have your drugs, cytotoxic and cytostatic drugs. There is a mistake. There is no epsilon here. It should be a S. You have resistance you have competition. And now, how do you see, if you put space, how can you see the drug? So the drug comes from the blood vessels which are around the tumor. That's what we explained at the very beginning. The tumor is growing from one event, a mutation event, and it's growing far away and it pushes, by the way, the tissue around it, so it pushes also partly the the blood vessels. So the blood vessels has tendency to come from the nutrients, the drugs and the oxygen come from the surrounding. So what you get in the middle is just the diffusion of the molecules, nutrients or drugs, plus consumption. So the cells, whatever is their phenotype, consume energy to survive, oxygen. So what you get for the concentration C epsilon is this. Okay, so this is a concern. Okay, so now I remember. Okay, I'm sorry. The C epsilon is the oxygen here in this model. This is C epsilon is the oxygen, so the nutrient, and the cytotoxic drug is here. But it should be also coming from an equation like that. But I simplified the model as much as possible. Okay, so now, depending where you are in the tumor, the level of oxygen is not the same. So your phenotype and your capacity to resist is not the same. Okay? So what you observe... Yeah. Sorry?
R of Y.
Yes. So this is... Oh, thank you. That's the rate. That's the rate would depend on this Y. Okay. And the radius. Okay. We need more letters. I always say that we need more letters. So, yes, thank you. So depending where you are on the radius, you will get a different level of access to the nutrient, and this changes the balance between these terms. So what is proved is that in that case, what you select is for each location, you select a phenotype adapted to the level of oxygen. So you have a Dirac mass with a certain weight depending on where you are, but you always select the fittest. Okay? And the difficulty in that in terms of mathematics is that in Y you like to work in measures, in L1 if you want. If you think of this, it's L1. If for the rho, what you see are more traveling waves. It's more that you work in L infinity. And we have very few tools in functional analysis to manipulate these kind of spaces. It's not very usual, and so that is the difficulty to work on these models. So this is also full of, these issues are full of open questions. It's very, very little things are proved. What you observe is the following. Try to make it bigger. So if you so this is the radius. This is a Dirac mass in Y, not X. And what you see is that on the bond border on the radius, you select here for, so in that case, you select for a small value. So this is Y. So if you don't put nutrients, if you don't put cytotoxic drugs, you select for zoo. Okay, so let me see. Okay, so the movie is, so if you don't put drugs, you select for a low value of Y, very, very high proliferative. And when you put the drug, so now we increase the drug here, then you see that slowly you select more on the boundary of the tumor where the drug is coming. You select for highly resistant, most resistant cells. And you see that the X is increasing here. So the phenotype is becoming more and more resistant. While you're in the middle, you don't see the difference, because in the middle, in any case, the phenomena which is the most important is competition between cells. And so with our model, resistant cells are also more competitive. So you see always the same level of resistance in the middle. But on the boundary, you will select for either the cells which are very resistant, like here when you have a cytotoxic drug, or which are low resistance if you don't put the... And this is the Dirac mass. So you see that at each R, you have a Dirac mass for a certain level of X. So this is what you observe when you do numerics. So here you don't put the drug, so you don't need to be resistant. X is small, highly proliferative. The phenotype will be small, will be lower than 1/2 at least. Decreases, and then it will increase. So what you observe also, maybe not very well in this movie, but what you observe also is something else, which is here. What you observe here is that if you have no therapy, your phenotype now is distributed. So this is the heterogeneity which is observed in experiments. You have a certain heterogeneity, which is not really an heterogeneity. It is the fact that it's in space, you have different phenotypes. So if you look globally, it's you have heterogeneity. And what you observe is that if you put therapy, you have also heterogeneity, but it's much more peaked. Here it's much wider than that. And it's also a phenomena which is known in biology, is when you increase the pressure, the selection pressure, you also decrease the heterogeneity. You select for more precise phenotypes. So when you have no therapy, you have more heterogeneity than with a therapy which is selecting for more strongly. So this is this point of view on this question of resistance to therapy, and this point of view that cancer is an evolutive disease. It's not only a disease based on principle of mechanics. It's also a disease which you have to see in the view of Darwin evolution theory, because this plays a role, and this is observed in principle in medicine. Okay, so we'll stop here maybe now. What I wanted to show in this course is that departing from questions from medicine, from biology, you can build up mathematical models which are really challenging in terms of analysis nowadays. You have these questions which come and which are basically difficult because you have many scales in this problem, so you have to always parameters which are small or big, depending on how you see them. And so you need asymptotic analysis, and you need asymptotic analysis with singularities. So it's not that it's smooth limits, as we see it's full of discontinuities everywhere. And one of the most difficult subject is that you have systems. Biology is always complicated. You need to handle systems, and whenever you handle systems, you lose all these tools, all these beautiful tools I showed you during 2 hours. You lose them when you have systems, and it's really challenging to find tools to handle them. There are many, many other questions, which may be more from the computational point of view, which I didn't speak about, but one of them, they are around these questions of variability and parameters. in biology, it's very rare that you have access to parameters like in physics. In physics, you know what is the speed of light. Who doesn't know the speed of light? You all know the speed of light? Who knows the speed of renewal of your nose? You know how many days you need to renew the cell of your nose? It's 15 days. So it's more important to know that your nose is renewed every 15 days than the speed of light, but you don't know it. Okay? And yes. Yes. Oh yes, that's because these are all these soft tissues which are which are in contact with the external has to be renewed very strongly. Your intestine is renewed every 2 days. I mean the out layers, not all the internal layers, but the external layers are reduced very quickly. Yeah. Your heart is renewed very, very slowly. Maybe 1 or 2% in your life. Only. Okay, but all these are different. I mean, every individuals are different, so we don't want to compute with certain parameters. We want to compute with a distribution of parameters. And for those who are computing, it's not to solve one of these PDEs that you want to do. It's to solve these PDEs with coefficients which are distributed according to certain rules which are more or less known, but which are different from each individual. So whenever you want to do individual therapy, of course, you face the problem that a single individual is not exactly like the neighbor. So all these questions are also important in terms of computation, and I didn't touch them. But there are many, many other questions which are very different because you are in the world of biology and medicine. It's very different from the world of physics. So I stop here. Thank you very much for your attention. And these are pictures of people who have been working with me on all these questions. Noemi was here last week. Tommaso also, he was young at the time. And Marcus also was here. No, of course, questions are welcome. And if you go to see your friends who do PhD in medical science or in biology, I'm sure many of them will be interested to speak with you. Some of them will say, no, I don't care, I want to do my experiments. But many of them will be interested in mathematics. It's surprising how they are reactive now to mathematics. So the only place where I see the evolution, the time scale is when you speak of evolution and you see many, many generations to see the evolution of a phenotype. Then that time scale is important. Oh, yes. The treatment, I mean, the failure of the treatment, and when cells have been adapting. So after enough division so that you have killed all the cells which are the target of your drug, and the other one have developed. So it's matter of, let's say, yes, weeks or month, let's say.
Asian young people, they are very shy.
Yes,
so
yes.
I have some question on behalf of them. Okay.
Yeah. Oh, no, they are very different. They're very different, completely different. No, yes, okay, the view I give seems to be everything is the same. No, it's very, very different. All organs are specific features that you have to put in the model if you want to be realistic. Very clearly, very clearly. For example, the most clear is skin cancer. Obviously, for skin cancer, access to oxygen is not an important effect because it's in contact with oxygen. If you think of another organ, the access to nutrient or oxygen is important. So it's not at all the same features that you will see if you do one or the other. Okay? And the form also, the shape also of the tissue is very different. The brain as a tissue, one of the reasons brain cancer are difficult to cure is that the shape of the brain is made of fibers. Very it might be, I don't know, yes, but certainly you are correct. Yes, certainly you are correct, yes. Yes. Yeah. No, this is a rough, you are absolutely correct. This is a very, so when you say this is a direct mass, you lose a lot of things. And you see it mathematically, by the way. But the limiting equation, this Hamilton-Jacobi equation I showed, in fact, doesn't give you all the information. If you look at it, you just get the information of the trait. You get only the Y bar. You don't get anything more. But if you think, but a biologist will ask you what are the mutations around that, what is the distribution of the population? I guess the fittest he can measure, he can see. So what he is more interested in is a distribution around that. So clearly, this is a mathematical point of view, which explains what you see, because it tells you why you see this sharp front, but the reality is the sharp front is a Gaussian. It's not a direct mass, for sure. Yes, this is a point of view. Mathematicians always think that the truth is a limit. In fact, no. A biologist will tell you, no, the limit is just an approximation of the truth. That's a different idea of what mathematics says about something. Yeah. That was a continuous number of nutrients. All these pictures are with a continuous number of nutrients. Yes, absolutely. Yes, that's absolutely. When you put a continuous distribution of nutrients, then you will still select for very specific. No, it will stay like that. I mean, the top one is stabilized, and the second one, I think, is also stabilized. No. Usually it will stabilize. It will be like that. It will never give. Okay, it's also again it's Turing instability. All these models, in fact, are Turing unstable, which means that the constant state, the continuous state, whatever it is, the continuous steady state is unstable. So we'll never see it, in fact. And this is because the equation is linearly unstable. So you have to see patterns. It is again related to Turing stability in some way. I mean, it's a little bit complicated to explain it, but it's related to that. So we will never see. Okay, it depends on the parameters, of course, but in practice, that's what the interesting cases are like that. But there are cases where you can find continuous distributions, but with unrealistic parameters. No, the difference are the number of. No, it's the difference is competition. When you do that, what you write is a dtn equal r of yn minus, and the competition, you write it like a competition, the competition between y and y prime, n of y prime dy prime, and this is minus n. Okay, so so individuals have a food, and they're in competition with the others. Okay, so you can play on this function and this kernel. So you have a lot of choices. And so to be all this, I think this is quadratic, just to make simple. And this I don't remember. This depends. This is the difference between the two pictures. But that's easy to put on a computer and see what is going on. It's a funny game. I did it to do that. I did it very roughly. I just computed with the quadratic cost. But in 1D you can do it. For computers today, it's not a problem. You can do it. It's not very expensive. I don't have it here, but we compared with Monte Carlo simulations, because in biology they have also codes based on Monte Carlo simulations. So all this we compared the continuous model, this kind of equations, with an agent-based model, and they fit perfectly well. So you can fit completely the stochastic model of the PDE. They are completely compatible. Of course, because mathematics tell you it's true, so it's better than the numerics also recover it. But yes, you see it. And it's Monte Carlo is much more expensive. You put, of course, you need to put many agents to recover this. But this is a game. It's. Yes. To the. Yes. Not necessarily. That is transport equations. Then you create and it's when you really create an equation dtn minus divergence nv equals something, and you have really a transport equation. So V you have to see it as an external field given by the second equation. It's not when V is a function of n, it's a self-contained equation which is parabolic. Here it's really becoming hyperbolic in the sense of finite speed of propagation. It's really a transport equation. So that's what I mean by hyperbolic. And the tools you use to handle that are tools from hyperbolic equations. Some people did it. Evelina Zatorska did it with Nicolas Vauchelet and maybe Pierre Degon in Imperial College when they were there. They studied the same question with Navier-Stokes equations. Yes, you can do it, yes.
Ask him question. Sorry, ask him. hears from you. But I know you early time you have a lot of problem in PDE, computing and neural analysis. At some stage, you suddenly change to mass biology.
Yes.
So to work with biologists or medicine people, what kind of they are from different worlds, some mathematicians. So what kind of advice to young people if you work with applied scientists?
Okay, yes, that's true that my background was more in fluid mechanics and kinetic equation than in the hyperbolic world. The reason I decided to speak with biologists was two reasons. The first one, if you remember well, in the year 2000, there were questions what will be the new challenges of science in the future, and many people were saying biology and medicine will be there. And I believed it. I was convinced that there were not enough mathematicians working on biology. And it was especially true in France. If you look in France, we have many universities. I think we had 90 universities 20 years ago. Now I think we have 60. But I would say in all math department, you would have people working on physics. I mean, physics is hard. I mean, fluid mechanics, quantum mechanics, there are many things in physics. But I knew only 2 universities in France where you have people working in biology. And so I said, okay, I know physics is important, but is it true that it's only 2 against 60, the ratio between physics? There is something wrong there. And so I decided that we should begin to really think about biology and medicine.
Of course, at 2000, you are already famous. You can switch a direction very easily.
No, it was very long. No, it was very long. Don't believe that. It was very long. Very long to do it. So what we did is first to read papers, because in North Europe they were more used to math biology, so we read these papers of Odo Dickman and all these people who were doing biology, were leaders in biology. We worked on them, and it took a long time to get contacts with biologists, to speak with them. They were not used to speak with mathematicians 20 years ago, 20 years ago. It was new for them. And so they were not at all at ease to speak with mathematicians. Now it's easier because there is a larger community of people doing that, and you have to learn the language. Well, the words are different. The words are different in math and in biology. It's surprising, but it's really, you don't understand the same thing with the same word. So it's also very long to do that. It was not so easy and so short.
Some of juniors, well, they have a tenure track position. MS, there are so many areas.
Ah.
And how for them, right? And I'm sure many of us, how to choose a area.
That I don't know. I would say if you can have, one of the questions is to have really contacts with people. If you want to do work, I don't know, in social science, okay, but try to find people in social science with whom you can work and can speak. And that's a major difficulty. The major difficulty is really to find real problems. I think mathematicians alone in their office and library will not find the same questions as someone in applied science. They will ask different questions. It's not that one question is better than the other one, but they will be different, so it will be funny.
They always follow their supervisor, they always read a paper, from paper to paper. From your side, how to find a real problem?
That's another question. Then okay, that's okay. I have no answer to that. The real problems, I don't know where they come from. But I would say when you speak with someone applied, either from physics or from biology, it doesn't change. they will have precise questions you cannot imagine by yourself. I mean, the data will, or the application will specify the questions. And I'm convinced that if this is something coming from some reality, there will be an interest in mathematics at some point. Because these are real questions, so there should be specific answers to understand, which are not those which are available.
What about some you guys have?
Okay, in any case, we'll be around.
Yeah. But if not, okay. Well, if not, it's like very great tutorial today. Of course, many details you need to figure out yourself from notes or something tell you this is a lot of questions here, there, but you need to find that yourself to figure out all the detail and the direction yourself. Thank you.
Yeah.